In this collection of videos, we will introduce our final concept from number theory, a very useful piece of information, sometimes called Bezout's identity. Before I state what Bezout's identity is, I want us to get a feel for how we use it in practice. And I'd like us to do that with some examples first to make it more concrete. So I've given you 4 examples below of integers that I've identified as a and b. Then, what I'd like us to do for that fixed a and fixed b is play a little game. Letting s and t be any old integers that your heart desires, what I'd like you to do is try to find the smallest positive value of the form a times s plus b times t. Remember, s and t need to be integers in this process. Then I'd like you to think about 2 things. First of all, is your answer unique? And second of all, can you actually prove that the answer that you found is optimal? So take a minute, pause the video, play around with these integer linear combinations of the a and b values that I've given you. For example, 5 times 0 plus 7 times negative 1, or something of that nature. Play around and see what the smallest positive value is that you can come up with for these 4 examples. Welcome back. Here are some examples that I came up with, and I wanted you to take a look. So for the first example, I was able to entirely win the game because I've written 1 as 5 times 3 plus 7 times negative 2, 15 minus 14. That's definitely equal to 1. And because I'm trying to find the smallest positive value of this form, and I have something of this form that is the smallest positive integer that exists, I know that I've won. So can I prove that I've found the optimal answer? Yes, because I was able to get 1, and that was the smallest that anything could be. In terms of if my answer is unique here, absolutely not. You quite possibly have a different example on your sheet of paper. Another example that I can come up with right off the top of my head would be 7 times 3 plus 5 times negative 4, and that would also get me an answer of 1. So your answer should be 1 here, but the s and the t values you found might be different. For number 2, a similar story is true. I was able to write 2 in a very easy way, 6 times 1 plus 4 times negative 1. However, I might be a little bit less certain that I've found the optimal answer. I don't just get it for free, like I did about the first one, because theoretically, 1 could be an example here. Maybe I could have 1 is equal to some linear combination of 4 and 6, and I don't know if maybe I just wasn't clever enough to see it. Now, most people will see, in fact, that 2 is the optimal answer here in a fairly nice way. Both 4 and 6 are even numbers. If I multiply them by any old integer, they're still going to remain even numbers. So if I have an even number plus an even number, the resulting number has to be even. That proves that 1 is not even a possibility for number 2, so 2 would truly be the smallest that I could get, and I do in fact get a 2. Again, these answers are not unique, the 1 and the negative 1. You may have other examples. For 3, we know that we've won because we have an example here. 21 minus 20 will give us 1. And last but not least, we have 4, which I think is somewhat interesting. For 4, I was only able to get 3 equal to 15 times 1 plus 6 times negative 2. Here, the reasoning that I've used so far has fallen apart a little bit because I haven't gotten 1, I haven't gotten 2, both of these numbers aren't even, so I'm going to have to be a little more clever to understand something like 4. Maybe you do understand it, and that's wonderful, but what I'm trying to do is lead us to Bezout's identity and this general phenomenon that we're going to have. So the next exercise that I want you to do looking at these a and b values is take a look and say, is there any way I could predict what number I was going to get here? And is there anything I can say about how I would have predicted what this number was based on the relationship between the a and the b values? So pause and take a minute to think about that before I reveal the answer that we get from Bezout's identity. Here it is. It's talking much in the nomenclature that we had on the previous slide. If a and b are positive integers, it's the greatest common divisor of those two integers that is the smallest positive number that can be written as an integer linear combination of the a and the b. Or in other words, it's that GCD of a and b that can be written as this as plus bt, and that is the answer. That is the smallest positive integer that can be written in this way. Now, where Bezout's identity gets particularly interesting, and sometimes what you'll only find written as Bezout's identity, is that if a and b are coprime integers, remember the definition of that, that means their GCD is 1, then 1 can be written as this integer linear combination of the as and the bt. So looking back at this first page, 5 and 7, well, they're both prime, and in fact they're coprime, so we got a 1 here. But example 3 existed to show you that it's not really the primeness of the numbers that was important, as much as it is the coprime relationship between them. This also solves the answer of, why was it 3 that I got as the answer over here? Well, 3 is the greatest common divisor of 6 and 15. The last thing I'll say in this video is that it doesn't quite seem like it from the way we've worded Bezout's identity, but remember that this is actually a biconditional statement. That is, if two integers are coprime, then we can write 1 as an integer linear combination of those two numbers. And conversely, if we can write 1 as an integer linear combination of two numbers, then we can conclude that those two numbers are coprime. So it's not stated like an if and only if statement, but you truly have both directions of that, and we use both of them equally and plentifully in abstract algebra.